Good day and welcome to my YouTube channel. I am Arthur Francis Devan. Please, you have to do some justice by subscribing and press the like button. In our last class, we were talking about organic chemistry. We've done the introductory aspect of alkanes and all it entails. I gave us the general molecular formula of CnH2n plus 2. We talked about some of its reactions, combustion and substitution reactions, which we have exhibited. We will also talk about the classes of carbon, the primary, secondary, tertiary, and quaternary. And through the general molecular formula, we are able to determine the molecular formula of all the members of alkane, which is the methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonadecane, and so on. So today, we're going to start from the isomerism of alkanes before we now move into alkenes, God willing, then into alkynes. Now, what is isomerism to begin with? Isomerism is a phenomenon where a compound having the same molecular formula but different structural arrangement. The molecular formula is the same, but the structural arrangement is different. Now, I will take a practical example. Let's take butane, which is the first member in the alkane family, or the lowest member to exhibit what isomerism. Let's see how that works in that case. We have butane is C4H10. Now, it means we have 4 carbon atoms and 10 hydrogen associated with it. Now we say isomerism is a process where a compound has the same molecular formula but different structural arrangement. Let's see how many structures we can get from this. Let's take the first one. 1, 2, 3. Then I have 1 here. I also have 1, 2, 3, and 4. So here, if I put my hydrogen, good. Now, remember I told us earlier on that carbon is tetravalent, which means it has 4 bonds surrounding it. This carbon has 1, 2, 3, 4. This one, 1, 2, 3, 4. This one, 1, 2, 3, 4. It is important you know that. So now, if I count C4, 1 carbon, 2 carbon, 3 carbon, 4 carbon, I have 4. Let's see the hydrogen to be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this molecular formula of butane, I have my C4H10. The structure here is different. Let's look at this other side. 1, 2, 3, 4. The same 4 carbon, hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see, we also have H10. Now, what do I say again was isomerism? A phenomenon whereby a compound having the same molecular formula but different structural arrangement. The structure here is different from the structure here. That is isomerism. And there are many cases where we can have 2, 3, 4, 5 isomers. So the first guy here, which is the butane, this is C4H10 for butane, and we have this straight chain for butane. We call it N-butane. N-butane, which means normal butane. But in this being the normal butane, this now is an isobutane, an isomer of butane. So we're going to check another compound to see how many isomers we can get. So we've gotten our first one from this. Let's take the second one. Remember, in our case, our general molecular formula remains as CnH2n plus 2. So let's take hexane, for example. C6H 2 times 6, 12. 2 times 6, 12 plus 2, 14. H14. So this is our molecular formula. Let us see the isomers we can get from it. 1. I put 1 here and 1 here. Now, 1, 2, 3, 4, 5, 6. It is 6 carbon atoms. 1, 2, 3, 4, 5, 6. 6 carbon atoms. 1, 2, 3, 4, 5, 6. 6 carbon atoms. 1, 2, 3, 4, 5, 6. 6 carbon atoms. The hydrogen. Well, I will put them for the sake of those of you who may be watching our lectures for the first time, but we have masterminded a method whereby we can, with this, we just proceed. We know that hydrogen atoms are associated with each carbon atom in a manner which gives us tetravalent. So let's just put it for the sake of that. I have So in all of these cases, we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 for this. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in all the cases we have what? C6, H14. So all of them still give us what we call our isomerism. By definition again, I say an isomerism is a phenomenon whereby a compound have the same molecular formula. The molecular formula is 6,6H14, but different structural arrangement. Their structures all are different, but all of them have 6,6H14. So this is what a pure example of the various isomers we can capture here so far. So this one is N-hexane, normal hexane. This one is 2 methyl This is 1, 2. In carbon 2 we have 2, 2. So this is 2,2-dimethyl butane. While this is 1, 2, 3, 4. This is 2,3-dimethyl butane. So we have done the naming, how to name the various compounds in our previous class. In case you have forgotten that, you have to go back to it so that you will not be lost. So in the course of naming this one, at least it will be faster for us. So that is what it is. We just have to show isomerism before we move to alkene. Now remember, if I give you another one, let's quickly, before I move further. If you were to be having C7H16. Now, what do? The first one, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This is our normal heptane. Don't mind the hydrogens are not there, but now I want to break it down. You understand what I mean by that? Now, what do? The best way to get isomers, if you cut one of these, you put it anywhere, it has given you one isomer. You cut 2 of these, you put them anywhere, it gives you another isomer. You can even cut 3 based on the length of the chain and put them, know how to fix them. It gives you another isomer. Let's take that is N-heptane. Let's take that, I'm cutting 1. 1, 2, 3, 4, 5, 6. That one I cut off. This is where it is. This is 2-methylhexane. That's my first word, isomer. Now I want to cut 2. 1, 2, 3, 4, 5. I'm having 2. 1 here, 1 here. This is 2,3-dimethylpentane. I have another isomer. I want to cut the same 2 again. Let's take it that way. 1, 2, 3, 4, 5. That same 2, but this time I put them in the same carbon atom. I have 2,2-dimethylpentane. Then I can still break it further. I can take out 3. If I take it, I'll be left with 4. This is 4. And I have 1 here, 1 here, and 1 here. My parent chain is 1, 2, 3, 4. Or 1, 2, 3, 4, whatever it is. So I can name this as 2, 2, 3 trimethylbutane. Because in carbon 2 I have 2, and in carbon 3 I have 1. So this becomes 2, 2, 3 trimethylbutane. All of these are isomers of what? Heptane. So the best way is you break the bond and attach it continuously. You continue to get as many compounds as possible. All of them are isoheptane, but this one is N-heptane, normal word, heptane. So these are isomers formed from what? Heptane. Alright, the business of the day. We want to deal with the alkenes, the few reactions it undergoes, and isomerism, and the rules of naming what the alkene family. So let's say that quickly. I can take this one out. Before I do that, I'd like you to tell me the number of isomers you can get. It's an assignment. You send the answer to the comment section. I will see into it. The number of isomers. How many isomers can you get from octane, which is 8 carbon atoms? Do it and send it to me. I will confirm the number of isomers you can get there. So let's take alkenes. Now, in alkanes, we say the general molecular formula was CnH2n plus 2, and all members of the alkane family were replaced with ANE. So if I have butane, this is butane ANE, because butane. Now, in alkenes, all the members will be replaced by what? The ENE. We use it to replace them. So we start with the first member of the alkene family. We do not have that method. We have 18 as the first member. So I have 18 propene, butene, pentene, and so on and so forth. Now, how do we know how many carbon atoms and hydrogen atoms will be there? Remember, the alkenes are unsaturated hydrocarbons, which means they have double bond between their carbon atoms. So let's start. Their general molecular formula is CnH2n. This is their general molecular formula. So if we use this, let us see what do we get in 18. 18 means 2. Am I right? So now I have C2H2 times 2, 4. Propene, C3H2 times 3, 6. Butene, C4H2 times 4, 8. And 5, pentene, C5, 2 times 5, 10. Now, let us see how do we draw their structures to show that this is a tin propene butene. We say they are unsaturated, they have double bonds between their carbon atoms. Let us move further and see that. 1, 2. Now, this is 2. I have 4 hydrogen atoms surrounding it. In our case, which are saturated, this is one bonded. But in a tin, it is double bonded. So if it is double bonded, the hydrogen will be placed this way. This becomes what? Our 18. Now, we say carbon is tetravalent in nature. It means it is surrounded with 4 bonds. So let's say this is 1, 2, 3, 4 for this. 1, 2, 3, 4 for this. And that's how the trend goes on. That is 18. What about propene? 1, 2, 3. We put our double bond. We put 1 hydrogen, 2, 3. If you don't know, some students will now put 4, 5, 6, 7, and 8. I think this is the structure because from the knowledge of the alkenes, this is what you were supposed to get. But once you do that, you become wrong. Why? Because propene is 3 carbon atoms but 6 hydrogen, and we have 8. Now you begin to check which of them is having more than 4 bonds. This carbon has 1, 2, 3, 4, 5. So take out 1. You have 1, 2, 3, 4. This carbon is balanced. This one, 1, 2, 3, 4, 5. Take out another one. 1, 2, 3, 4. This is correct. This one is 1, 2, 3, 4. Correct. So now if you count 1, 2, 3, 4, 5, 6, our hydrogen are now complete. But if you don't have that formal knowledge, obviously you're going to put these things there and think you're good. At the end of the day, you'll be wrong. So don't forget, carbon is tetravalent. So if that is for propene, let us see for butene, which is 4. 1, 2, 3, 4. I can put my double bond here. when we get to isomerism, we'll know why it can be in the middle or here. Whenever, okay, maybe I should just explain that. Whenever the double bond is between the terminal carbon means the carbon at the end, the beginning or the end, the terminal carbon, you call it, this is butene. Normally, if it is here in the middle, the double bond is in the second carbon atom. 1, 2, yeah, 3, 4. So this becomes 2-butene. Either you call it 2-butene or but-2-ene. It depends on the one you like. So this is 2 because the double bond is in carbon 2. We call it but-2-ene or 2-butene. We are good. Now, if it is in the terminal carbon, you don't need to tell us 1-butene. 1-butene is still correct, but you don't need to tell you. If you just call it butene, we know that it is in carbon 1. Propene doesn't, all of them are terminal. You call it pentene, hexene. We know that the double bond is in carbon 1. But if it is not in carbon 1, it is in 2. You tell us 2-butene, 2-hexene. It is in carbon 3 heptene, and so on and so forth. So let's proceed. When we get into the naming process, you will know how to name that, and also the isomerism procedures that will be associated with it. Alright. So now that is for butene. Now the hydrogen atom, butene is C4H8, we've gotten our C4, the hydrogen at 8. First, I have 1, 2. 1, 2, 3, 4. This guy is correct. Now this one is 1, 2, 3. It needs 1. 4. This is 1, 2. It needs 2. This is 1. It needs 3. 1, 2, 3, 4, 5, 6, 7, 8. So this is what? Butene. It is very important you don't make those mistakes. You will see them when you start dealing with questions on your own. Let's look at pentene, which is 1, 2, 3, 4, 5. Now I put my double bond here because it is normal, the first 1 pentene, but we'll call it pentene normally. If it is here, it becomes 2 pentene. But then, let's see the hydrogen atom, how they're going to fit in. So I have my 1, 2 here, 3, 4. This carbon is balanced. This carbon here has 1, 2, 3. I put 1 here, 4. This one has 1, 2. I put 1 and 1 here, 4. 1, 2, 3, 4. 1, 2, 3, and 4. So this is the structural formulas for the various ethene and alkenes, which we have made mention of: ethene, propene, butene, and pentene. Okay, let us move further into reactions of alkenes. Alkenes undergo one distinct reaction that differentiates it from alkanes. That is what additional reaction. Now, when we're talking about alkanes, remember I told us about the substitution reactions, which is peculiar to alkanes. That reaction cannot be carried out by alkanes. Why? Because alkanes are saturated hydrocarbons. They have one bond, one single bond between their carbon atoms. Now, if you were asked what is the difference, a cardinal difference between alkanes and alkenes is that alkanes undergo a substitution reaction while alkenes undergo additional reaction. This reaction makes them unique to that end. So alkanes cannot undergo addition, and how do you call them? Alkenes cannot undergo substitution. So now we want to carry out what? The basic reaction. Of course, all of them undergo combustion reaction. So let's start with the combustion reaction of the alkene first, which is unique to both saturated and unsaturated. We used methane before to show that. Now we're going to use ethene to show the combustion reaction, which is unique to that. Then after which, we now have to go back to the addition reaction to see how can we do that and the mechanism therein. We use one mechanism to show how that can guide us to doing everything we want to deal with in terms of what additional reaction. So, alright, I said reactions of alkene first, combustion. So alkenes, we have C2H4, am I right? 1, 2, 3, 4. Good. Plus oxygen will give us our CO2 gas plus water. So let's see how then can we balance this equation. We have 4 hydrogen, we have 2 hydrogen. If I put 2 here, hydrogen is 4. Hydrogen is balanced. I have 2 carbon, I have 1 carbon. If I put 2 here, carbon is balanced. Okay, let's see if that's true. But oxygen, we have 2. And we have 4 plus 2, 6. So if I come back here, I put 3. Oxygen becomes 6. Oxygen here is 4 plus 2, 6. Hydrogen is 4, hydrogen is 4, carbon is 2. So like this, the reaction is balanced. This is combustion reaction, which is a basic reaction of all hydrocarbons. They undergo combustion. That is why they're born in what? Air. If you bring your petrol down, light it up, you see how flammable it is. So all of them undergo combustion reaction. So now, the basic reaction that differentiates the double bond and the single bond, which is the additional reaction of alkenes. Let's see that. Now, in that reaction, let's take our alkene, the first member, which is this. This is it. Now, additional reactions, we have the halogenations, which means it reacts with halogens, chlorine, bromine, iodine. We have hydrohalogenations, which is hydrogen and halogen, or hydrogen and iodine, halogen, or hydrogen and halogen. This is hydrohalogenation. We have halogenations. So any of them, hydrogenation too, reaction with hydrogen, with this. So all of this can be added with the alkene in the additional reaction. So we're going to take just maybe 1 or 2 to see how that works. Let's start with hydrogenation, which is the first one. So the first additional reaction is called hydrogenation reaction, plus hydrogen 2. Now, let me expatiate with this hydrogen. This hydrogen molecule, the ring, can still be written as this. That means that hydrogen dot and hydrogen dot. This and this come together through this bond process to give us this. And this is the same thing as this. Now, something happened. The mechanism, like I said, that's what I want to deal with. I want to show us the mechanism in the first reaction. Then you're going to use that principle to discuss or deal with the rest of them that we encounter. So let's take this. I want to replace this with this. So you'll be able to see what happens. Remember then, this, let me put it there first. So this is hydrogen molecule. Now, when an element gives out one of its electron, it becomes short of 1 electron. We want that sign, if it is short of an electron, become positively charged. And that guy that gained the electron that came the ring become negatively charged, become having what? Excess electron, become minus. So here, this is what happens. Because in the course of this reaction, this hydrogen the ring will react them here to come. Okay, let me react them first. Doesn't matter, anyone. So this guy will give us this. It moves with one of its electrons. And let's say this one can still go this way. That's the mechanism. This is what happened inside that you don't see, that I want to show you today. So we have this, our hydrogen here. I now have 1 bond. This is my, let me take it this way. My hydrogen here. Now that excess that came in will make this to become negative. And this one that gave out 1 bond becomes positive. The same thing happened here. In the hydrogen, this one has given out, it becomes positive plus hydrogen negative. In physics, we're told that similar charges repel, different charges attract, which is a rule of nature. Man is never attracted to a man. Man to man will repel naturally, unless if that is being bastardized by some diabolical means. So here we go. This is it. Now, this is positive, this is negative. They are meant to come together. So this will move here. And this is negative, it will move to the positive. Don't mind me, the movement, whatever. So this is what you get. So when that happens, what do we get here? We now have, remember this hydrogen has come to the place here. So this becomes, I have one hydrogen, and now hydrogen. This hydrogen has come in here. And I have a single bond here with hydrogen here. This positive comes to the negative side and this gives us this. And down that gives us what? A tail. So hydrogenation of alkene gives us what? An alkene. Hydrogenation of ethene gives us a tail. That is the principle. And that is natural. So at every instant, a question may come like, the hydrogenation of propane will give you what? Hydrogenation of propene will give you what? A, propane, B, butane, or whatever it is they want to give to you. But you should know that it will give you what? Propane. Because it was propene, the double bond, one of it will be stripped out to give you a single bond. So whenever hydrogenation takes place, if it were a double bond, it becomes a single bond. If it were a triple bond, like we see in the future in the alkyne procedure, it becomes a double bond. You go undergo again, it gives you a single bond. Now, why do I have to show you this? It is very important. Let me show you in the next reaction which I want to carry out to see why I have to show you the mechanism and where the various hydrogens will belong. So, if I can clean this, let's take another example. The same ethene reacting with hydrohalogenation, which is HCl. So I will have this. This is my hydrogen, plus hydrogen and chlorine. Now, we want to react this. In the course of our reaction, how will you know if this chlorine, because we know in the reaction it's supposed to be either in this carbon or in this carbon. Now, how will you know that this chlorine will be in this carbon or in this carbon? You can only know that if you understand the principles of what the mechanism of reaction. Otherwise, you can put it anywhere. And there will be instances where the knowledge of that will become very valuable that you cannot do without it. Alright? So now let's see how it can only be here if in the course of reaction this give out its own electron, perhaps it becomes positively charged and this is negatively coming in here. Or if this one gives out, this becomes positive and this is negative and it comes in here. This is very electronegative, more than hydrogen in the course of that. So let's see if I can take this out. Alright, if I do that again, permit me, this time let's go this way. And this will always go to the negative chlorine because it's highly electronegative, more than that of hydrogen. So now I will have here, I have this here. Okay, let me take it down, please. This is negative because it gives out its one. This is positive. And here I have hydrogen, which is positive, plus chlorine, which is negative. And I should know that chlorine will come in here because this is negative, this is positive. And this is positive, it will come down here. So if I know that, I can easily proceed by showing us that this is my hydrogen, negative, positive is going there, hydrogen will be here. And I have hydrogen, and chlorine will be here. So that is chloroethene in that case. I will carry out another reaction, but this time around I'm not going to be showing the mechanism. I only use this so that we understand what to do or what is required of us in case. So let's see what we get this time around. I'm not going to show you that, but let's see how we get in. Alright, now I want to use something like pentene. Pentene is C5 H10, if I'm not mistaken, plus this. And my C5H10 is the same thing as saying this 1, 2, 3, 4, 5. I put my double bond here. Put my hydrogen here. Here. Yeah, 1, 2, 3, 4 for that. Hydrogen, 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 and hydrogen. That's good. Plus HCl. I will just have my 1, 2, 3, 4, 5. The other one will be gone. Now, don't forget, this chlorine must come to either this carbon and never this or this. Why? Because the reaction is taking place in breaking this bond, so it can either come here to make it negative or here to be negative. So if in the course of you bringing your chlorine and you put it anywhere here, you're wrong. Just have to, your bond, you fill it directly. So it must be this carbon or this carbon, the carbons that have the double bond. I want to show you this so that we'll be able to, so we'll be able to see how that works again in another compound. So this is it. 1, 2, 3, 4, 5. Now I have my chlorine here, I have my hydrogen here, hydrogen, hydrogen, and so on we go, just like that. So remember it was an alkene, but now it is not an alkane, and this is 2-chloro. It is in the second carbon. This is 2-chloro, 1, 2, 3, 4, 5, pentane. In that case, let's see this kind of the same reaction, but differently. So if I have my 1, 2, 3, 4, 5, I have my double bond here now. My hydrogen, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 3, 4, 1, 2, 3, 4. Now this is reacting with HCl. Okay, this will now give me 1, 2, 3, 4, 5. Now my chlorine will come in either here or here. Let me now put it here. So here or here, so I decided to put it here, as the case may be. The rest will have hydrogen, hydrogen, hydrogen. So this is 1, 2, 3, 1, 2, 3, 3-chloropentane. So you have seen in the same kind of compound, it's just based on the positions of the double bond. We'll talk about that in isomerism. You have been able to see that here was 2-chloropentane and now here becomes 3-chloropentane. You must now know that the position of the Cl is dependent on the double bond. You don't put it anywhere else other than the double bond. Anywhere outside the double bond, you are completely out. And your instructor will obviously feel you for that. So you must take note. It is very important. So we can do these reactions over and over and over, as many as we want to do. We continue to get the same thing. So let us advance further and see what else we do. Let's go to isomerism. Isomerism of alkenes. Now, I said isomerism is a phenomenon, a process by which a compound having the same molecular formula but different structural arrangement. Now, in double bonds, we have three types of isomerism. We have the positional isomerism, we have the structural isomerism, and we have the geometric isomerism. All these are exhibited by the double bonded compound. Let us see how. We're going to take some questions in relation to that, but then let's see what is the positional isomerism. Positional isomerism is just the difference in the position of the double bonds. For example, if I have 1, 2, 3, 4, 5, I have my double bond here. This is pentene. 1, 2, 3, 4, 5. That's pentene. Now, another isomer of this can become base 3, 4, 5. 1, 2, 3, 4, 5. This is 2 pentene. If I have 1, 2, 3, 4, 5, 6, for example, and I put it in the middle, this becomes 3 hexene. 1, 2, 3, 4, 5, 6. It can be here, which is hexene. It can be here 2 hexene. It can be here 3 hexene. So that is what positional isomerism, which is based on the position of the double bonds. So you can do that as many as possible. Now, structural isomerism has to go with the position of the double bond and the structure. Take note, the position of the double bond and the structure give us what? Positional isomerism. Let's take an structural isomerism. Let's take an example of that. So I have a compound 1, 2, 3, 4, 5. This is pentene. I want to get an isomer of pentene based on structural framework. I now have 1, 2, 3, 4. I still have my double bond here. And I cut one of these and put it here. This becomes 1, 2, 3 methyl butene. Alright? 3 methyl butene or but1E if you want to put it that way. So this is it, because this is a structure. It's different from this, obviously. And I can still have another one to be 1, 2, 3, 4. I have my double bond here. Okay, this is 1, 2, 3. And I still have my C here. This is CH3. Don't forget that. So if I come from, this is 2. Alright? So I have 2 methyl but2ene. Because this is 2 butene. Alright? And my 2, the methyl is in carbon 2. So I have 2 methyl, 1, 2, 3, 4. 2 methyl but2ene or 2 methyl 2 butene. So this is also a structural isomerism. We should the structure to be different. Alright? And now the last one is geometric isomerism, which is very peculiar to double bonded compound. Let's see an example of that quickly. I have this. Let me put it this way, and this. Okay. Now, in geometric isomerism, we have 2 forms of arrangement. We have the cis arrangement and the trans arrangement. Cis arrangement means the supposed substitute or thereabout are arranged in the same manner, in the same side. While trans, they are arranged in the opposite manner. Let me take this, for example. If I want to write this in terms of geometric isomerism, I have my double bond here. These 2 carbon atoms are having that. I have this and I have this. Now, remember this is CH3. This is 1, 2, 3. 1 hydrogen here. 1 hydrogen here. And this is my CH3 here. Now, what is the official name for this? This is 2-butene. Okay? Because the double bond is in the second carbon atom. So it's 2-butene or but2ene. Now, because of this position of base, this becomes what? Trans. Remember, because this CH3 is opposite to this other side, it becomes trans. Alright? This becomes trans 2-butene. Alright? This and this are in opposite direction. So let's see the C so that you will get it right. You will not mistake it. If I want to write this in the cis pattern, I have this. I put my CH3 here, my CH3 here, hydrogen here, hydrogen here. So we see that the position of base is different from this. This one's are in opposite, this one is at the same side. So this becomes cis 6 means they're in the same side. 6, 2, butane. We can do this plenty, as many as we want. Let's take a compound that may look a little complex and see how we can arrange it in terms of cis and trans. Okay. Let's CH3 CH2 3 C C CH3 sorry CH2 CH3. Now if you look at this is a long somewhat compound. Let me take this one out. This is CH3 here, CH2 in 3 places, CH21, CH22, CH23. I have my C, I have my double bond, I have my C. Okay, I didn't put the hydrogen, sorry, hydrogen here. So there is hydrogen here, there is 1, 2. There is hydrogen here to CH2 and CH3. Now, if I want to position them in a cis and trans manner, this is what I can do. I will come down here. This is my double bond here. These two. And this hydrogen, this is the hydrogen. This is C2H5. This is an ethyl group. I'll come here and put my CH3, 3 of them, CH3, 3 of them, then CH3. So this is one, and this is another hydrogen. So you see that I've been able to arrange it in a trans manner. Alright? And this. I can still arrange this, bring this one up here and put it here in a cis manner. So that is how this thing goes. But what is the name of this compound? You come here, 1, 2, 3. The double bond is in carbon 3, 4, 5, 6, 7, 8. The parent chain is the octane chain. Double bond octane, perhaps. So this is 3 octane because it is 8. So in that form, so if you want to call this, you call it trans 3 octane because it is in the trans form. If I put it in the cis form, you call it 3 octane. Now, having said that about this, we now look at what we call optical activity. Now, optical activity is the ability of a compound to rotate a plane polarized light in a dextro manner to the right. We call it the dextro rotatory. To its right, we call it dextro. Now, for a compound to be able to rotate a plane polarized light, it must have what we call the chiral center, otherwise called the chiral carbon. The chiral carbon is that carbon that is having 3 or 4 substituents differently. They are not the same again. So now what are we talking about? We're talking about optical activity. Let's see what we do in terms of optical activity. And all optical activity are able to rotate a plane. They are plane. They can rotate a plane polarized light. We have a compound. This is CH3. This is hydrogen. This is CH. Let me put it in front. Then CH3 here. This is bromine. Now, your job is to trace the chiral carbon, to know the chiral carbon. 1. We say a chiral carbon or the chiral center is that carbon that has 4 different group attached to it. Let's think, this is our chiral carbon. Now, this side is a methyl attached to it. This side is a hydrogen attached to it. This side is a bromine attached to it. And this side is an ethyl attached to it. So the four different guys attached to this carbon are different. They are not related in any manner. If I have hydrogen here, this carbon is not chiral. Why? Because it has two similar group attached to it. Then all the group attached to the carbon atom must be different. As such, we say that compound is optically active, because it means that it has the ability to rotate a plain polarized light when it passes through it. So this is 2-bromobutane. Another one, okay, let us see if we can trace our optical, the chiral compound, or the chiral carbon, sorry. So you have C2H5 here, I have hydrogen here, I have bromine. Okay, let's call it hydrogen. I have hydrogen, I have hydrogen, I have hydrogen, I have hydrogen, hydrogen, hydrogen. I have hydrogen, hydrogen, hydrogen. From here, which of the carbon is chiral? Okay, we want to know if this whole compound is optically active. Means we must be able to trace one carbon atom that has all the substituents or groups attached to them to it differently. Now, if you look here, look up. If you look into this compound, which one here do we say is optically active? Which one has a chiral center? Two, yeah?
No.
Yeah?
Yes.
Okay, let's look at this. It has an ethyl. It has a hydrogen. It has a propyl. It has a methyl. So this carbon is optically, that is the chiral center. Okay? So it's the chiral carbon. So therefore, this compound is optically active. That is how you know. What is the name of the compound? 2. Are you sure?
No.
Now, let's know if we are correct. Let me break this down. This ethyl, this is what it means. That is what it means. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. This is become the parent chain, not this. So you must first of all identify your parent chain. So this is how the parent chain goes. This is 1, 2, 3 methylhexane. Alright? You don't just because this is attached to this, you can't just say it's 2-ethyl pentanone. First, identify the longest chain, which is the parent chain, and that is it. Okay, we've talked about that. Let's go to the rules of naming. Rules of naming alkenes. Okay. General procedure for naming alkenes. 1. Select as the parent chain the longest continuous chain. Of course, we did that in the previous one. We must first of all identify the longest continuous chain of carbon atoms, which must include the 2 carbon atoms containing a double bond. In this case, our longest continuous chain must have that carbon that contains the double bond. You cannot take the parent chain or the longest without it having the double bond in it, even if it is longer than the other one. The one that has the double bond should be the one you consider first. Then, name it as that of the corresponding alkane. Example, let's take a particular example here. 1, 2, 3, 4, 5. This is pentene. Okay, let's see more. Alright, in that one, they said, since all the 5 carbon atoms form a continuous chain, its parent name is pentene. Why? Let's take another one. Okay, good. I think I have a nice one here. Now, in this one, if you want to get the longest, this is 1, 2, 3, 4, 5. Let's look up. 1, 2, 3, 4, 5 is the longest. But 1, 2, 3, 4 is our parent chain. Why? Because it contains the double bond. This one does not contain the double bond. So we cannot regard this as the longest, rather this. So the longest possible the parent chain must contain the double bond. So I have 1, 2, 3, and 4. 2-ethyl butene, because the double bond is in carbon 1, or but 1 in, if you want that. Okay, 2-ethyl, the ethyl is in carbon 2, butene. Let's move further, and so we can name more. Now, assign number 1, 2, 3, which I've done serially to the carbons in the parent chain, such that the first carbon containing the double bond is given the lowest possible number. Yes, regardless of the position of the constituents on the parent chain, like I've illustrated. Now let's take, if the position of the double bond is unaffected when the parent chain is numbered forward or backward from any direction, it is not different. If you name from this right side, you have maybe 2 butane. You name from this side, you have 2 butane. Well, once that happens, now they say the parent chain is numbered forward or backward. Yes. Preference is then given to the position of the substituent, for instance. So you now have to consider the substituent that attached to it and give preference to that. Let's take a particular example here. Okay, I think it's 5. 1, 2, sorry, it's 4. Okay, if I put it here, CH3. Now, the double bond, if I come from here, 1, 2, from here, 1, 2, both sides, this is, the double bond is in carbon 2. But now, since from both sides, it gives me the same, preference should be given to the substituent. The substituent, if I want to consider the substituent, it is in carbon 2. But from here, 1, 2, 3 is in carbon 3. So the preference will be given to the side that has the lowest possible, which is 2. So therefore, 1, 2, 3, 4. This becomes the order of what? Numbering. So this is what? 2-methyl 2-butene. Or 2-methyl-but-2-ene. Are we good? That is the double bond, so pay attention. When naming a substituted alkene, such substituent will, with its number separated by hyphen, becomes the prefix to the parent name. For instance, let's take another example. Okay, it's just the writing format. Okay, let me write it out. Let me finish. For instance, a particular example will be taken in this form. I think I've illustrated it before, but let's just take it again so that we'll see what they want. Now, 1, 2, 3, 4. 1, 2, 3, 4. Double bond here. 1, 2. Okay, so since there is a substitution there, substituted alkane, 1, 2, 3, 4 is our parent chain. So what they are telling us is, this is 2-ethyl, 1, 2, 2, 3, 4. 2-ethyl, but 2-ene, or 2-ethyl 2-butene. The one you like best, you deal with that. Alright? So you must separate them with these hyphens. Use this to separate them. That's what they're trying to tell us. Okay, in the case of further cases, there is no need to specify the position of the double bond since it must be on the terminal carbon. Like I've told us earlier on, if we have pentene, which means the first carbon atom is in carbon 1, you don't need to tell us 1 pentene, just tell us pentene, we know. The double bond is in the terminal carbon. And so forth and so on. When there are 2 or more double bonds, the parent chain must contain as many double bonds as possible. Even if it is not the longest continuous chain, the number assigned to the position of the double bonds must be as low as possible. The word ADI, ATRI is then added to the ending in. In place of in, you add ADI for 2, ATRI 3, ATRA for tetra, ATETRA, and so on. Let's take an example here. Example 8, where are you? Okay. Okay, this is now let us identify and so on. Now, that is what let's say we should add when we have double bonds, or 2 double bonds, or triple bond as the case may be. Now from here, I have 1, 2, 3, 4. I have double bond in carbon 1 if I come from here, I have in carbon 1 if I come from here. So it would have been from any direction, it wouldn't matter. But I'm considering this side as 1 because the ethylene group, ethyl group is attached to carbon this side, so it gives preference from here 1, 2 than coming from here 1, 2, 3. So I come from here then to say 1, 2, 3, 4. Lowest possible locant as the rule has commanded. Now, this is the second carbon atom. I have an ethyl. So I have 2 ethyl. Remember that in the place of, instead of butene, they say you should change this to this. Okay. Now let's see how does that work. Now this is 2 ethyl buta. Okay. Since they are double, okay, sorry, let me come. 2 ethyl 1, 3, 1, 3. The double bond are in position 1 and 3. 1, 3 butadiene. This is the ADI they say should add. Because di means there are 2. There are 2 diene. Okay? Now, we have, in carbon 1, we have how do you call it? An in group, a double bond, which is in. We have another one, which is another in. So we have 2 ins. So in chemistry, when you have 2, you call it di. So we have di-in, 2 ins. So now the diene are in position 1 and 3. So it becomes 1, 3 diene. But the chain is butane. So they said you should take that. Normally it would have been butene. We replace this with ENE. They say no. When you have double bond, instead of EN, remove this and put ADI. ADI. So instead of butane, it becomes butadi. Since there are 2. If there are 3, it becomes butatetra. Butatetra. Okay? Butatetraene and so on, if it is ever possible. But it can be 4 tetra. So we have to extend the chain to get that. Alright? And so on and so forth. So that is how the whole stuff keep going. And that is how we got this. So let's take another practical example and see how the di and the tri can work. If I have 1, 2, 3, 4, 5, 6, 7, double bond, double bond, double bond. So if from here 1, 2, 3, 4, 5. 1, 3, 5. 1, 3, 5. Here is 2, 4, 6, 10, 12. This is 9. So I start from this side. So it's better 1, 2, 3, 4, 5, 6, 7. So now let's see. In this case, 7 is called heb. It's supposed to be heb. Okay? Not supposed, it's heb. Heptene, if it is one double bond. Okay, and so on and so forth. So let's position them. 1, 3, 5.
1, 2. Let's try.
Now, how many? Heptatriene.
Yes.
Okay, that's 7. So 1, 3, 5. Heptatriene. There are 3 in. So the ATRI now comes in because there are 3. The way there are 3, bring ATRI to replace this place, which would have been heptene. ENE. You remove it and put ATRI. So it becomes hepta for 7, buta for 4, penta for 5. Then you bring the in inside. Heptatriene, octa, whatever it is. And we're going to see a lot of that. But it's cardinal important if you know how to name them. Okay? Questions like this will always come. A whole question will be like, name the various organic compounds. And you keep strong. If you don't have the basic rules, you're going to miss out. Okay, let's take another interesting one I'm seeing here. It's nice. Now, 1, because of bromine is in this side, so this becomes preference comes from here. So I now have this to be 1, 2, 3, 4, 5, and 6. Now, 1, 2, 3 bromo, 3 bromo, 1, 3, 5, 1, 2, 3, 4, 5, 6. Instead of hexane, become heza. Heza, there are 3 bonds. Triene. Are we following now? Good. So with that, we continue to move on. It becomes easier. Am I right? Yes. Let's take another one. They say we should give the allopath names of the following compound. How do we name this? Let's look at the board. What do you think is the name? The parent chain is 4 for butene, and we have a substituent in carbon 2, so that's 2-methyl butene. Another one. Now I can clean, I guess. Okay. Now again. 1, 2, 1, 2. Because of the substituent being this, I can start from the 1, 2, 3, 4. Am I right?
Yeah.
This is 2 chloro. 2 chloro what?
No. 2 chloro.
2 chloro 2 butene.
Okay.
Or 2 chloro 2 put 2 in. Alright? Let's take another one. Write the structures and the IUPAC names of the following compounds. I'm going to give us a compound. Let's write the structure and the IUPAC names, alright? Okay. These are condensed structures that we have to expand them. Here is CH3. Here is C, it has its hydrogen bonded to another C. Of course, we should know that, okay, it doesn't give us tetravalent, so it must be double bond here. So this carbon. Now from this carbon, we have CH3, 2 of them. So I have CH3, CH3, 1, 2, 3, 4. So we're good. Now, you see we should name. If I come from here, the same, 1, 2, 3, 4. So I will always come from here because the substituent is here. So this becomes my 2, right? Yes. So now I have 1, 2, 3, 4. 2 methyl, put 2 in. 2 methyl, put 2 in. Or 2 methyl, 2 butene. Let's take one or two more. Alright, quickly. The first C, H, and there is a V are attached to it. It's bromo. I move down to the second C, I have 1 hydrogen. Move down to another C, I have 1 hydrogen. Of course, there will be a double bond here effectively for 1, 2, 3, 4. 1, 2, 3. Now, to this other side, it comes a CH2. CH2. Then the last one is CH3. There are 2 CH2, then CH3. So this is it. Now, 1, 2, 3, 4, 5, 6 is what hexane. But the double, we have a bromine in 1 carbon 1 and a double bond in carbon 2. So 1 bromo, 2 hexane, or 1 bromo has 2 in.